Hello everyone. This video covers section 5.8, extrapolation methods for differential equations. We have done extrapolation twice already, in chapter 4 and in chapter 3. So to refresh your memory, in chapter 4, I believe it was in section 4.3, we talk about Richardson's extrapolation. This was used to find integrals. Now again, remember that m was the integral you want, so you should check again 4.3 to check that. So this is the integral that you want to find. Okay. And 1h is the numerical method. So this is the method we're going to use. And all of this was the error. And obviously the dominant error was this. So this specific method, the error is of O, big O, H. Now here the method 1 n1 of H is whatever method you decide to use. Remember in chapter 4 you have multiple methods. One of them was the trapezoidal. The other one was Simpson's. You also have the forward differences and so forth. So any method that can be written in this form, you can apply this extrapolation technique. Remember that the technique requires to do the following. This is the original method. Then in the same method, you go from h is replaced by h over 2, which will give you this now. This one still has order O, big O of h. However, if you multiply this one, remember this is the method, so this will give you n1 h over 2, but now this will be k1 over 2 h plus k2 squared over 4 and so forth. Again, we have done this before. And then if you combine these two, you can get rid of the h, so this will be gone. And when you do the algebra, you end up with something like this. This k2 is not the same as k2, so this k2 is not the same as this one, but it's just a constant. And by doing the interpolation here, now this one is O of h squared, so you improve the accuracy by doing this. Where n of h2, once you combine this and solve for n, it was equals to this. Okay, so again, this is just a review of what we did before. What we're going to do in this section is very similar to this. Again, not the same thing, but very close to this. We're going to use exactly the same technique that you did before. So the method we're going to use here is going to be the midpoint method, which we have done before in 5.4, I believe. So therefore, we're going to have something that looks exactly like this or this, but the method is going to be the midpoint method, which is precisely this. So this is the difference equation. Now notice how here I is more than equals to 1, so the first value you're going to get here is going to be w2. So you are skipping w1, which you may need for the next step. So therefore, you have to be careful with that part, because the information you get is this. You're always going to get the initial condition, which is usually denoted by this. So this is the initial condition, which is technically always given, otherwise you can ask to the problem. However, you're gonna need also W1, which you don't have or is not given, but you have solved these methods before, so therefore you can use Euler's method. You can use other more complicated ones, but since you only need an approximation, the easiest one to use is Euler's method. So just use Euler's method, and that's how you will get W1. And then all of these will be the difference equation for the midpoint method. Therefore, this method is going to be the basis to the solution of the problem. And remember, we're still trying to solve this. This hasn't changed. So this is the problem that we want to solve. And obviously YT is the solution. So the solution is going to have this form. So notice that this is technically what we were calling N1. So you could think like if this is N1 of H, so this will be the method, which will be the midpoint. And then this is the error, which is technically the same as this right here. Here the values for delta 1, delta 2, and delta 3 do not depend on H. So delta 1, delta 2, and so forth don't depend on H. And here we're assuming that H is fixed. All right, so let's see how we do the extrapolation using the midpoint method. All right, so what we want to approximate is y of t of 1. So just think of this way. We start in t0, which is the same thing as value for a, and you want to go to t1. And the distance from here to here is h. So clearly you can see that t1 is just a plus h. Now we're going to need to find two approximations, and then you're going to combine the two approximations to do the actual extrapolation. So this is how this is going to go. So let's say that for the first approximation, this is step 1. So for this one, you let h0 to be equals to h over 2. So you divide by h over 2, which is exactly the same thing you did in chapter 4. And then we're going to use Euler's method. Okay, the beginning of chapter 5, Euler's method, with the initial condition, which was W0 equals to alpha, to approximate you're going to approximate y of a plus h0, which is the same thing as y of a plus h over 2. So h0 is right here on the middle, and is equals to h over 2. So obviously Euler's method implies that W1 is going to be W0 plus H0 f of A W0. Remember that A is the same thing as T0. Now in step 2, you're going to apply the midpoint method. So midpoint method, uh, with ti minus 1 is equals to a, and ti is equals to a plus h0, which is the same thing as just a plus h over 2. So then from here you find y of a plus h, which is equals to y of a plus 2h0. So notice that this is w1 and this is going to be w2. So therefore from here w2, you use the method, is going to be w0 plus 2h0 f of a plus h0, and then w1. Then for step 3, you want to do something kind of new that you haven't seen before. So you're going to do something that is called the end point correction. So you need to correct the endpoint here. And the formula is going to be this, and this is the one we're going to be using. So y11, so this is going to be the endpoint correction. This is going to be 1/2 w2 plus w1. By this point, you already found w2 from here and w1 from here, plus h0 f of a plus 2h0 and w2, which is an OH square approximation to y of t1. Now, once you get y11, okay, once you get this part, then you automatically get rid of w1 and w2. So you don't need this anymore. Okay, just like when your friends use you to get something, once you get there, they don't need you anymore, they don't talk to you anymore. So this is gone. So the only thing that you need is this. Now for the second approximation, we're gonna do pretty much the same thing, but now here you want to get y of 2, 1. So it's gonna be the same process, very similar, but instead of getting y11 is going to be y21. So the steps are very similar, and just like we did in chapter 4, so for step 1, we're going to divide h over 2 or h over 2, so therefore the new h, which we're going to call it h1, is going to be now h over 4. So again, we're going to use Euler's method with the initial condition w0 equals to alpha, just like before, to approximate y of, okay, let's see, to approximate y of a plus h1, which is the same thing as y of a plus h over 4. And remember, the approximation, if you use Euler's, is going to be w1 is going to be equals to w0 plus h1 times f of a w0. Also notice that we still have the same interval. You still start at t0. You still want to end it at t1, but now the increment is going to be h over 4. So this will be 1h over 4, another h over 4, so this will be 2, and this will be 3h over 4. And then the distance from here to here is still h. So now this will be w1. So now you're going to also need w2, w3, and w4. Now again, in step 2, we're going to do the same thing. In step 2, you're going to again apply the midpoint method. And if you do that, you need to get now W2, which is going to be W0 plus 2H1 f of A plus H1, and then W1. Then you're going to need W3, which is going to be now W1 plus 2H1 f of A plus 2H1 W2. And then finally W4 is going to be W2 plus 2H1 f of A plus 3H1, and then W3. And then finally on step 3, we do the same thing. You need to find the end point correction, okay, or you apply the endpoint correction to the method, but the endpoint correction is applied only to the last 2 points, so it's applied to W3 and W4. So therefore from here we're going to have y of 2, 1 is equals to 1/2 W4 plus W3 plus H1 f of A plus 4H1, and then W4. And this will be the new value. So again, you can forget about W2, 3, 2, and 1. And the one you're going to need now is just going to be this one. So this will be the second approximation to YT1. So again, this is an O2 approximation to Y of T1. All right, remember that YT at the very beginning was equals to WTH plus delta 1 H squared, delta 2 H to the 4, and so forth. Remember also that A plus H was what we call a T1. So therefore this is an approximation, this is the error, and in fact this is order of H squared, which is just this one too, okay, and so is this one, okay? So here we got 2 approximations for Y of T1, Y11 and Y21. If you expand this will be Y11 plus delta 1. Remember, delta 1 is just a constant. This will be H squared over 4 plus delta 2 H to the 4 over 16, and so forth. This one will be Y21 delta 1 H squared over 16, and then again delta 2 H to the 4 over 256, and so forth. Now here, if you do a little bit of algebra and you combine this and this one, you combine both of them, then from here, so you will get the YA plus H is going to be equals to Y21 plus 1/3 Y21 minus Y11. And you can see the similarity between this and section 4.3. Then minus delta 2 H to the 4 over 64 and so 4. So you can rewrite this as y22 minus delta 2 h squared over 64 and so 4. So here you have where y22 is equals to y21 plus 1/3 y21 minus y11. And you can see that this approximation now, this one is of order h to the 4, which is essentially what the same technique that we did in section 4.3. Now you can keep doing this to change it from oh to the 4 to oh to the 6 and so forth. So if you keep going, you will get the following table. So you can see that this was the first approximation we did. Then we did this one. y21 combines these two. Then you can do the same thing with y of 3, 1, and so forth, and so forth. It's exactly the same thing we did before. All right, so let's do an example where we apply this, and this. All right, so we gonna go to the usual example. Y prime is equals to y minus t squared plus 1. T is between 0 and 2, and the initial condition is y0 is equals to 0.5. Here, clearly we have that w0 is equals to 0.5. T0 is equals to 0, which is technically just the value for a. And let's say that h is equals to 0.2. So this has to be given, and remember once it's given, this value is fixed. All right, so the first thing we need to do is we need to find y11, but remember before we do that, we need to find w1 and w2. Okay, so if we follow the steps that I told you before, so for step 1, h0 is going to be h over 2, which will give you 0.1. Then to find w1, remember you need to use Euler's, the regular Euler's method. And this should be w0 plus h of 0, f of t0 w0. And if you plug in the values, this will be 0.5 plus 0.1 times 0.5, which gives you 0.65. Then for step 2, we're going to need the midpoint, and that will give you w2. So w2 is going to be w0 plus 2h0 f of t0 plus h0, and then this is the w1 you just found. So it will be 0.5 plus 0.2 times 1.64. So you should check all of these computations, and this is just equals to 0.828. Then remember for step 3, you need to find the endpoint correction, and the endpoint correction, the formula is the following: y11 is equals to 1/2 w2 plus w1 plus h0 f of t0 plus 2h0 then w2, which once you plugging all the values, this is around 0.8284. And again, you should check this. Remember that this is an approximation. It's an approximation to y of 0.2, and the approximation is OH squared. All right, so then remember for the second approximation, you need to find now, so now we need to find y21, and this one you're gonna need a W4 and W3, so it needs W4 and W3, but you have to follow pretty much the same steps. So for step 1, the new H1 is going to be now H over 4, which in this case it will be 0.005. And then W1 is going to be equals to W0 plus H1 F of T0 W0. Remember that this one uses Euler's method. And when you plug in all the values, this will give you 0.575. Then for step 2, you're gonna use the midpoint to find W2, W3, W4. And remember W2 is gonna be equals to W0 plus 2H1 F of T0 plus H1 W1, and once you plug in all the values, this is 0.65725. Then you need W3, which is going to be W1 plus 2H1 F of T0 plus 2H1 W2. Again, once you simplify, this will give you 0.739725. And then finally, W4 is going to be W2 plus 2H1 F of T0 plus 3H1 W3. And this is 0.8289725. And then in step 3, you can find y21. So y21, you use the corrector, the endpoint corrector. The formula, remember, is 1/2 W4 plus W3 plus H1 F of T0 plus 4H1. And then this is W4. So this will be 1/2 times 0.8289725 plus 0.739725 plus 0.05 times F of 0.2 times 0.8289725, and all of this gives you around 0.8290730625. So finally, the first extrapolation result. So extrapolation result is going to be y22, which will be y21 plus 1/3 y21 minus y11. And once you plug in the values, this will be 0.8292974167, and that's it.